Can everyone hear me? Great. All right, so I'm Brett Cunningham, and I'm going to talk about memory analysis during incident response. Thanks, Patrick. All right, got the giggles back there. So what is memory analysis? It's basically taking a look at RAM, taking a look at the artifacts that it's just in temporary memory. And in this talk, I'm going to speak to mostly what my abstract was about. I didn't have enough time to completely hit all of it. But we're going to take a look at basically moving beyond the basics, which generally speaking is just using strings. Also take a look at what artifacts that we can look at more intelligently that reside in memory. Data structures specifically that help you put the full picture together, and how they pertain to the incident. So we've got things like network connections, typing on the command line, and the residue of injected processes. So anyone here do incident response besides that back corner? All right, and those two. Got stragglers. All right. So we're going to go with the absolute beginning, where when I first started, I didn't know what I was doing. This is even a step beforehand. So what happens during incident response is you want to dump the full contents of everything in RAM. All right, HP Gary has a tool that does this called FD Pro, and it will dump it into its compressed file format. I had no idea what I was doing, so when I was told to run strings against that, I ran strings against that actual compressed file format. Nothing came out. All right, so what I'm doing here is the strings minus EL. This command history is the raw dump of everything in memory. The EL is a combination to include Unicode in there, and then I'm grepping for telnet. So here, why I'm grepping for telnet is to see if the attacker had typed any commands on the command line with telnet. And we see here that they telneted to this IP address on port 1234. All right. Problem here is that we have all this extra information that really doesn't make sense. It's left over from the telnet program running, and just other junk. So to go a little bit more intelligently with that, we want to take a look at data structures. And can anyone here describe what a data structure is in a very simple term? All right. I kind of struggled a little bit when I first learned about it, but it's used by programmers to create a little bit more advanced variable type. So if I want to create a variable called movies, it's going to have all these members that belong with it. So we're going to have a variable called title. It's going to be of type string, an actor string. So the name of the movie is going to be a name, which is generally what a string is. And the year, it's going to be of type integer. An integer is typically just a number. All right. The price is going to be a float. That's a number that can get some decimals after it. All right. So we end up declaring a data structure by saying movies, Star Wars. So Star Wars is going to be the name of our new data structure. So that's the name of the data structure. The data structure type is movies. If you want to know what the background of movies is, you have to come back up to where you declared what the structure of your data structure is going to look like. So to put a little bit into perspective, if you wanted to create that movie data structure and then assign the title, it would look like movie.title equal Encino Man. The main actor being Pauly Shore, the year and the price. So this right here would be the data structure type of movie. All right. So in Windows, whenever you create a new connection, specifically this one's a TCP connection, it creates the structure type of TCP/T object. And underneath here, it defines everything that belongs to that data structure. Here we can see easy ones that most of us, I think, are familiar with. Remote IP address, local IP address belong to this TCP object. The remote port and the local port belong to it. And then we've also got the PID number. So I'm going to use a program called Volatility to extract these data structures. Volatility is a command line program that helps you run through memory analysis more efficiently and quickly than using something like a debugger, and more intelligently than something like running strings. Here you see it just as a memory analysis framework. That looks a little cut off. There we go. All right. And we're going to run conscan. So this is going to look for any TCP object in memory. All right. Here, it gives us the offset into the RAM dump that it found the object. We have, as we looked at in the slide, we have the local, we had the remote IP, local IP, then we had the remote port, the local port, and then we got the PID number that it belongs to. So the PID being the unique process identifier that you typically see in something like Task Manager. And what's interesting is if we take a look at conscan, what Volatility essentially does is it opens up that RAM dump, which I did in a hex editor, and it will go through and look for specific, look for that data structure that's defined. And here we're just reading it in hex, but you can see that we have the declaration for a TCP/T object. So it's iterating through this file, looking for basically the start of the structure, and then everything's defined in the structure right here, and it starts ripping out all the details. And that's simply when you go through and type in a command like this. That's what it's basically doing in the background. So it saves you a lot of time. Second command we're going to take a look at. If you remember, we were doing strings in Telnet. Do we know if the attacker went through and typed in any other commands? The only way to take a look at that is by replacing Telnet there with other commands. So you can end up building this huge library of commands and trying to run it against a file, but you saw how much junk we had there. Volatility has what's called command history. Yep. Command history was reverse engineered out of Windows in order for the Volatility crew to be able to extract the data structure. So there's no real pretty way to show this unless I made my own diagram, but obviously I didn't. But we are taking a look at this data structure called command history, and all the members of it are listed right here. So flags being one, list entry, application, and so on. All right. So it's command scan. There we go. And when we run command scan, it goes through and will pop out the commands that the attacker typed right here. So we saw the first telnet to 1234. If you guys looked carefully when I showed you that huge blurb of data, there was also the telnet to 81. But I mean, it was hard to see that when you get lost in all that data. We also see, an FTP connection outbound, trying to enumerate a little bit on the domain, change directories, and then finally, that's me coming in and dumping RAM into a file. Win32DD belongs to Moonsoul's memory, and basically, it's been a fantastic way to get a memory dump.
So these commands are in sequence, if we're going to look at it time-wise?
Yes. Yes. It should always be that case. I'm not sure if that's true, but these are, in particular. All right. You should see that it's typically always with csrss.exe because that's the executable in Windows that handles the Win32 console application. And just to briefly run through what it would look like if we were able to fully do this. By the way, I'm going to sidetrack real quick. Here with Task Manager, this is stored in a data structure in memory, what the processes are. And it's just called eProcess. One of the fields in the eProcess is the name of the process, the unique identifier, and so on, the commit usage and all that. So if it helps, just understand what a data structure is. I mean, this is kind of the best graphical view I can lay out. So when going through and looking for data structures, you can essentially use something like WinDebug, open up the memory capture, and list all processes. We can list all the processes with that command of pound process 0. And then we know that CSRSS, it always handles command histories. That's always the process that data structure is going to belong to. So we can find upwards in here.
Is that true on the PowerShell side as well?
I'm not there yet. Yeah, so anything with Windows 7, I haven't been able to confirm that. So this is for Windows XP and Server 2003. If we find upwards, we can locate our process. So the image name is CSRSS, and what we're going for is the process ID, which it's shown there. We can then switch to the process by typing pound or bang process, and then pass it the ID. Here we go. Okay, we switch there. And now it's showing us all the threads that belong to this process. Yeah, this is one example of a thread. So each one of those belong to the parent of CSRSS. And if this structure wasn't reverse engineered, if Microsoft had it outlined, we'd be able to run through all the threads, which I'll show you later on a little bit better example. I'll show you later on a little bit better example. But we'll be able to go through each thread and extract the data structures out of there. Oops. Okay. So that plugin was written by a guy named Michael Howley, I think. And If you guys recognize that name, it's because he wrote the Malware Analyst Cookbook, well, part of it. He's done a lot of work with the Volatility project and made things really simple. So we're going to sidetrack here and go to Timeliner. Timeliner was written by a gal named Jamie Levy. Her online handle is just Gleeda, Gleeda. And what she's trying to go for is pulling out timestamps of interesting artifacts from memory. The supported timestamps she has is the system date, process timestamp, so when a process is created, thread timestamps, network timestamps. So the thread belongs to the process. Network timestamps are any time that you create something like that TCP/T object that we talked about earlier. Registry key last write times, which are interesting, especially when you have a registry key that was written to one of the auto runs, so anything like current version run. If a program was included into that. And then some of the event logs for just XP in 2003, and then any PE timestamps, so some of the metadata that you get from Windows executables, such as an EXE or a DLL. How she did this was that she borrowed some commands from Volatility already that were already in process. So we have it's called PSList and PSScan. Should show you. PSList goes through, finds a process, and then tries to enumerate all the other processes. So it's essentially like Task Manager. And you see here that we have the time that it started. PSScan is essentially the same thing. It takes a little bit longer, but it goes through and it ignores information from the operating system and really goes through the entire file and tries to see if there's any other processes. So what that's really helpful for is in trying to look for some kind of rootkit, something that's trying to abstract itself from being found in Task Manager. So she went through with Timeliner and used the eProcess create times, eProcess exit times. For thread scan, it's the create and exit times. For the plugin sockets and NetScan, use sockets create time. More formatting required. Don't remember what I mean by that. So we're going to take a look at the output. This is how you run it. Just call Timeliner, pass it to Volatility, and give it the image name and the output file. One thing of note here is Timeliner does not run on the latest development branch. It's locked in at 2.0. Otherwise, you get some pretty nasty errors. And just let it run. It takes forever. So I had gone ahead and ran it. So here we see a couple of the different modules. Or when I went through and said, and she borrowed, eProcess.createTime and all that, we see here we get the time frame, what kind of data structure was dumped here, the name of it, and then some of the additional information. You see here, we've also got socket types, the event log. An event log is really short, so I think what's happening is when the event log is written, it hangs out in memory until that area needs to be used again. So it's freed up, but when memory is freed, it doesn't immediately get overwritten. So she identified the structure of that and is just capturing it. Because you see that this event log, generally speaking, it will go on for a long time. and that was only, what, 2 pages. We've also got thread, and it will, part of its data is showing the parent ID that it belongs to, so the process ID, and PE timestamps. Last one should be way down here, the registry. I'm not entirely sure how much of the registry it covers, but you see we're 6% through the file. Yep. Okay, so registry keys just started. We're 6% through the file, and it continues to go down forever. So what I need to do next is either ask her or just compare to see if there's what the differences are. And why we're doing this is during any kind of incident response, memory is the very first thing that you want to capture. It's the thing that's the most volatile. It's going to change. Anything that you do on the computer is going to change the memory. So you grab that, and it's going to be real interesting to see how much data we can extract from the memory before we're waiting for the rest of the logs to come in. Yep, so the last thing that we're going to take a look at is injected processes. Yep. And how we do that is by looking at what's called the virtual address descriptor. Yeah. The virtual address descriptor is a tree-like structure that it's basically a tree that hangs upside down. You have your VAD root, so the very beginning, and it continues to branch out. What this describes is the pages that are actually being used in memory. Windows waits until the absolute last minute before it creates any memory page. So if a program says, hey, I'm going to need 512 megs of memory for my program, and it asks that up front, Windows doesn't do it until that program actually attempts to write there. So the VAD is describing what is actually being used. Yeah. So in VAD parsing, we are walking the VAD. So we're going through each process's tree. So every single process has a VAD. And what we're going to take a look at are the 2 Windows API calls that are infamous for process injection. It's virtual alloc ex and write process memory. And what those do is they create a VAD page of the type mmvad short, and it has the permissions of page, read, write, execute, and no cache, which I didn't put that on here. But we'll see that in a second. Other valid pages, page types can be mmvad or mmvad long. So you have 3 types, and what you just have to know is that virtual alloc ex and write process memory, since they are used for process injection, the left behind artifacts that they have is that it's of mmvad short and page, execute, read, write, plus no cache. So I've been experimenting with Volatility's shell lately, and it's been cool. We enter into the shell by calling Volatility and just saying vol shell. And it will give us an interactive command line program. Has anyone used something like Python's interpreter or IRB for Ruby? All right, it's very much like this, and it's in Python. It uses Volatility's modules and classes that they defined. So PS will give us a process listing. I've already kind of cheated because this is going to suck if we go through every single one. I know that explorer.exe is one that I'm interested in. Since this is Python, we could just iterate through every single process here and look what we're looking for. So I'm going to change to the context of explorer.exe by saying change context and then giving it the PID number of explorer.exe 1096. Okay. And then volatility is kind of cool because it will describe the E-process structure when you call upon it. So I just asked volatility. I go DT, and then give me the E-process structure. You can do this with other data structure types that Windows has defined. In here, you have create time, exit time. Those belong to E-process. Active process links, quota, and all that. The interesting one that we're going to come down to is the VAD root. This is a pointer of where in memory the first committed page is. Well, the data structure of VAD root, which will then lead us to where the first committed page is. For this process, we switched using this command. We changed to the context of explorer.exe. So I want volatility to fill in the values of the current process's data structure. So by issuing DT, then self.eproc, this says for self, meaning the current process, give me the E-process structure with all the values filled in. Here you see the create time. Exit time hasn't occurred yet. And then we come down and we see VAD root. VAD root is a pointer. So I want volatility to now give me the information of the data structure of VAD root for the current process. So current process, all right, then it goes to VAD root, and it's now printing out with this, it's now printing out the data structure and the values of it. Here we can see the tag is VAD-S, and then really the right child and left child are the ones that we're going to take a look at. Right child and left child show us this will describe to you the tree structure. What I'm doing right here is straight out of Volatility's handbook or whatnot. But when a command gets too long, go ahead and throw the value of that into a variable. The variable we're going to call VAD root. It'd probably be appropriate. Great. So now we're going to ask it to describe to us what's at VAD root at the right child. So at the right child, it goes and you see that it's another data structure that looks like VAD root. So these are all VAD nodes. That's what the data structure is. We can continue walking the tree by saying, go to the next right child. So we went from the parent, we had a decision to go to left child, right child. Now we went to the right child for you guys. And we got another decision to go to the right or left child. We can keep going down to the right child, and so on until we finally hit no other committed pages. And that will be of the value 0. So that's just how you navigate the VAD. Why that's important is we're going to now take a look at what the data member U has in it. So when we ask what's in, we navigated the page to find some node, and then we ask what's in U. We see that it's long flags and VAD flags. We're particularly interested in VAD flags. VAD flags is now going to show us the characteristics of that committed page and memory. We see a lot of like the commit charge, physical mapping, private memory. Some of this information you see and some of the more advanced use for a task manager. What we're really interested in is the protection level. The protection level is 4 here. That doesn't really mean a whole lot until you come back and you look up memory protection constants. So what does 4 mean? 4 here says page, execute, read, write. So that means that that page in memory is able to be read, written to, and if it can be executed. So if that contains code, the code will be executed. Now, we talked about the virtual alloc function and its ability, this is what the virtual alloc function looks like when you call it, and we have this called FL protect. FL protect, if we come down, will lead us to this page that says memory protection contents. Memory protection contents, we saw page, execute, read, write. But we're also curious about the artifacts that are left over in memory. So if you have not only the page, execute, read, write, plus the page no cache, we see here that in Microsoft's documentation that this is often, page no cache is often accompanied by virtual alloc EX. And quite simply, if we use Volatility's VAD info, so this will give us the info. I pass it along the PID of explorer.exe. Pass along the PID of explorer.exe, so I'm asking it to give me the information of every single VAD node that belongs to explorer.exe. So it walks that tree for me, which we just did manually. And now I'm looking for protection type 6. All right, the grep with the BA or the B2 and the A2 means give me 2 lines before, give me 2 lines after. So this puts in a much easier view what I want to see. So it tells us that in explorer.exe we have 1096, gives us the beginning and the end of the memory, or beginning and end of the memory page. The type of VAD it is. So VAD S means that VAD short that we saw earlier. And I said here, if it's a VAD short and page, read, write, execute, that's a leftover artifact from using virtual alloc EX. So now we just identified all the pages that have the tag of S, protection S, and in short, that is what malfind does. Command history. All right, we can run this command, and it goes through. it iterates every single process. It iterates, or it looks up the VAD root, then walks that VAD root to grab all the pages. Looks at the protection level and the type. And so Malfind goes through and it's trying to look for injected processes. It also does a lot of other things, but we'll skip that today. The output from it is a dump of all those memory pages. If we go into there, and just take a look, you can see it's just data. All right, so this data really doesn't mean a whole lot, but what's nice about Malfind is that it will help interpret it for you. It's going to assume some things about the architecture type and be able to interpret it for you. So it found a concerned process, or found a page in memory that it's concerned about. It tells you the process. It gives you some of the attributes about it, such as its page, execute, read, write. Protection level 6, so that means page, execute, read, write, plus that no cache. We looked that up in the memory constants. And then it will try and start spinning out the code segments. This should, right here, if I recall, be the page, one of the pages of the injected code in memory. So. All right. Yep. So that's absolutely it right there. We went through there. We saw the process that was injected into. We saw the characteristics of those memory pages that that made it interesting for Malfind. At the beginning, we just took a look at the data structures for connection scan, for the command history, and I hope you saw that it was 100% more reliable. Not sure I should throw that out, but a lot more reliable than using something like strings. So now I'm going to ask for any questions, and we got Jack back there. Thank you.
So, did it list the bad number or the page where that injected process lived? And if so, could you run strings against that page to, I guess, better determine what was injected into that process?
So it gives you the offset here, the address. I suppose you could go through, dump that region in memory using something just like a hex editor, carve it out, and then run strings against that.
I guess it would be one way to target that specific area of memory.
Yeah.
Where bad lives, I guess.
That's a great question. That's actually one method of being able to reconstruct binaries. So if you have a Trojan that was deleted off disk, but it's still running in memory, that's one way to reconstruct parts of it. So you can then give it to your reverse engineer guys. They can go through and tell you what they can glean from that little bit of information. So great question, thanks. Tim.
To answer the earlier question on Windows 7, the
Yeah.
command history is still under CSRSS.
Cool.
It's still launched. The structure changed slightly, but it's still there.
Okay. All right, great. I think command history written by Jamie Levy, I think that's still only for XP in 2003. But what Tim back there is saying is that the data structure type changed a little bit, but it's not too far off from what's currently in there and should be entirely feasible to still grab it. So.
Will the first command page always be that root?
Yeah, it should be. I mean, that's basically how Windows finds its way around memory that's actually been committed. So, yes.
Would process injection show up in a situation where you
detailed process tracking, auditing on the box, in the sense that, I mean, one of the things we do on higher security machines is enable detailed process tracking. So anytime a process starts on the machine, or does whatever certain operations, you're going to have that, which seems like it could be a shortcut for some of the early stuff here, but I don't know what the ability, for example, of rootkits and that kind of stuff is to sneak past detailed process tracking, or whether detailed process tracking might be pulling out of the same structs that.
Okay. I'm not sure how that works, but I'd love to look it up and see. So, yeah, let's talk afterwards. Yeah. Any other questions? All right, great. Thank you.
You got what? I did? Did I? It's not on. Is it? Oh, there you go. Okay. All right.